Okay, good morning, afternoon, or evening, everybody. Welcome to the Exploring Earth's Land Surface with Suomi-NPP VIIRS Land Data webinar. This is your host, Jennifer Brennan. And most of you have already noticed this, but while everybody's logging in, we have two optional polls located in the bottom left and middle portion of your screen, and we do appreciate your feedback on these polls. I've got 2 p.m. Eastern Daylight Savings Time, so we're going to go ahead and get started here. What I'd like to do first is review some of the logistics related to this webinar. To ensure the best audio experience, the conference has been placed in silent mode. However, if you have any questions or you have any issues, what I'd like for you to do is enter those into the Q&A pod, and again, you'll find that on the lower right-hand corner of your screen. This works like a chat. Today's webinar is being recorded, and the recording will be posted to our online Adobe Connect webinar catalog as well as to our NASA Earth Data YouTube channel within a few days of completion. And what I'll do is I'll send an email to all of the registrants with links to these recordings. In addition, today's presentation files along with some useful URLs will be provided to all of you and the presentation available for download at the end of the webinar. Regarding timing for today's webinar, it will be 1 hour long, and we've allocated 45 minutes to the presentation and live demonstrations with an additional 15 minutes for the question and answer period. Once our speakers have finished with their presentations, we'll then transition to an optional final set of polling questions, and then from there we'll move directly to the Q&A period. And then just one final note, depending upon the volume of questions that we receive today, we will extend the Q&A period an additional 15 minutes to 3:15 p.m. Eastern Time for those of you who may wish to stay on the line. During today's webinar, we will have 2 speakers. Our first speaker is Danielle Golan. She's a Science Communication Specialist at the NASA Land Processes Distributed Active Archive Center, or LPDAC, and that's located at the USGS AEROS. She will kick off today's webinar with an introduction to VIIRS NASA land data products, and then also provide 3 short data discovery and data access demonstrations that will, using both NASA Earth Data Search, VIIRS, and the LPDAC data pool. Our second speaker today is Cole Crable. He is a remote sensing scientist at NASA LPDAC, and he'll wrap up today's webinar with a live demonstration within Jupyter Notebooks. And through this demonstration, what he'll do is he'll show participants how you can work with daily VIIRS land surface reflectance data in R and Python. So with that, it is my pleasure to introduce today's speaker, Danielle Golan. Danielle?
All right, thank you, Jennifer. Let me share my screen. Great. So let's go ahead and get started. So as mentioned, my name is Danielle Golan, and I'm the Science Communications Specialist for NASA's LPDAC. And today I'm going to be talking to you about Suomi-NPP VIIRS land data. But first, I'd like to give you a little bit of a background about the LPDAC, so you know more about where these data are coming from. So let's jump right in. What is NASA's LPDAC? Well, we are the Land Processes Distributed Active Archive Center, and we're located at the USGS Earth Resources Observation and Science, or AEROS Center, in Sioux Falls, South Dakota. And the LPDAC was established in 1990, whereas AEROS itself was established in the 1970s. So we are one of the NASA Earth Observing System Data and Information System, or EOS-DIS DACs, around the country. And these DACs are part of the NASA Earth Science Data Systems Program. Some of the other DACs cover topics like snow and ice, ocean biology, socioeconomical data, but we specifically work with land data. And our hundreds of thousands of users range from students to professors, archaeologists to meteorologists, and everything in between. And the DAC itself has distributed over 17 petabytes of data to these users. And we have archived over 3 petabytes worth of data composed of 237 data products. And we have a lot more data coming down the pipeline over the next few months and years, so be sure to check back periodically to learn more about the latest data. And most importantly, all of this data is available at no cost through a variety of means. So where do these data come from? Well, our newest sensor is VIIRS, and that's what we're going to focus on today. VIIRS is the Visible Infrared Imaging Radiometer Suite, and it's on board Suomi, and it's a continuation of MODIS, which was a continuation of AVHRR. So similar to MODIS, VIIRS is continuously capturing data and providing a larger picture, but in less detail. So if you think about mailing a letter, it's going to cover the entire envelope worth of data. We also have MODIS, the Moderate Resolution Imaging Spectral Radiometer, and this is a sensor on board Terra and Aqua. And as I mentioned, it's pretty similar to VIIRS. We also have ASTER, the Advanced Spaceborne Thermal Emission and Reflection Radiometer, and this is a sensor on board Terra. So Terra and MODIS are actually on one of the same sensors. ASTER is taskable, meaning it has to be told to turn on. So we're seeing higher resolution data. If we think back to that envelope analogy, it's going to cover about a postage-sized stamp worth of area. We also have our NASA Measures products. So these projects expand our understanding of the Earth through already existing satellite measurements. And I think it's kind of cool that we're reusing these data in unique ways. And finally, we have the community products. So these are either derived from one or more NASA Earth Observing System or EOS missions, or sometimes they're data submitted by users. So today we're just going to focus on VIIRS. But if you're interested in learning about these other data, please visit our website, or you can let me know after this presentation, and I'll be sure to follow up with you. So here we have a comparison of the backbone missions of the LPDAC. VIIRS data are shown in blue, and we can see the spatial resolution is similar to MODIS with 500, 1,000, and 5,600 meter resolution. And the temporal resolution ranges from daily to monthly with several resolutions in between. And using this chart, we can see VIIRS has some similarities to the MODIS missions, and in a little bit I'll go more in depth to the similarities and differences between VIIRS and MODIS. But first, let's talk about VIIRS as a sensor. Again, VIIRS stands for the Visible Infrared Imaging Radiometer Suite, and it's located aboard the Suomi-National Polar Orbiting Partnership, which is a joint mission between NOAA and NASA. And VIIRS captures the Earth twice a day, so we're able to have copious amounts of data to help us understand what is going on the Earth. And while this is a joint mission, it's important to note that the data I'm talking about today are specifically created by NASA and distributed by the LPDAC. And as I mentioned before, these data are a continuation of the MODIS heritage. So if you are currently using MODIS data, we recommend looking for the VIIRS counterpart, if available, for your data to see if it meets your research needs. And these data have been collecting globally since 2011 to present, so they are available for time series analysis. And we're currently distributing 12 data products, but we have way more coming down the pipeline in the future, even as soon as the next couple of weeks and months. And the native spatial resolution of these data is 375 and 750 meters, which has been resampled to 500 meters, 1 kilometer, and 0.05 degrees to complement that MODIS heritage. And these data are gridded using the sinusoidal horizontal vertical, or HV grid, and they're archived with an HDF EOS5 file format. So I've touched on some of the differences between VIIRS and MODIS, but let's directly compare the two. So again, MODIS is on 2 satellites, Terra and Aqua, whereas VIIRS is on 1, the Suomi-NPP. MODIS was launched in 1999 and 2002, respectively, while VIIRS was launched in 2011 as part of continuing the MODIS heritage. VIIRS is about 119 kilometers, or 74 miles, higher in orbit than MODIS, so we're seeing less gaps in the data near the equator as previously experienced with MODIS data. And VIIRS experiences a similar equatorial crossing time with Aqua MODIS at 1:30 p.m. And VIIRS has 22 bands as compared to MODIS's 36 bands. These 22 bands include the visible reflective, near infrared, shortwave infrared, medium wave infrared, long wave infrared, and day and night. And the VIIRS native spatial resolution, again, is 375 and 750 meters, and they are resampled to 500, 1,000, and 5,600 meters for consistency with that MODIS data. And finally, the MODIS data are provided as an HDF4, whereas VIIRS are provided as an HDF EOS5. So now that we've discussed the sensor itself, let's talk more about the actual data. So these are the 4 categories I'm going to cover today: surface reflectance, vegetation, LAI and FPAR, and fire. And in a little bit, I will also mention some products that are going to be available in the future. So let's dive right in and talk about surface reflectance first. So when we are talking about surface reflectance, what do we really mean? Well, in a way, what we mean is that these data provide a bird's eye view, or maybe a mechanical bird's eye view, of the Earth. So we're able to explore and see what's going on the land surface of the Earth. And these data products are provided daily in 500, 1,000, and 5,600 meter resolution. They're also available as an 8-day composites in 500 and 1,000 meter resolution. And similar to most surface reflectance products, you can composite these layers to highlight and analyze different features on the land surface, for example, snow, ice, floods, those types of things. And one important thing to note is that these products have been corrected for atmospheric effects. Now, I'd like to take 1 second to explain what these VNP09GA things mean. You might be thinking these are secret codes, but they're not. These are actually the short names of the products. So the VNP stands for the VIRS products. The 09 tells us that these are a surface reflectance product, and the GA, CMG, H1, and A1 provides us hints to the temporal resolution. And you're going to see these short names throughout the presentation, so be on the lookout to learn what the short name means for the different data products. So now that we've learned about the basics behind the surface reflectance data, let's examine some imagery. So here we have a VNP09GA image of 2 typhoons, Typhoon Sulik and Typhoon Cimarron near Japan from August 22nd, 2018. So we have Typhoon Sulik and then Typhoon Cimarron. And actually, the very next day, Typhoon Cimarron made landfall over Japan. And with these daily products, we can not only observe these beautiful images like the one you see on the screen, but we can also observe changes over time. So for example, we can study the lives of these storms, so how they formed, how they churned, and how they dissipated. And on the other side of the world, we can examine how the landscape is changing. So here we have the Black Hills of South Dakota, with the city of Rapid City covered up by the clouds to the left, and the Missouri River to the right. And below that, we have the Badlands National Park. So let's watch what happens here. So in late June, there were 2 thunderstorms that rolled through the area and produced hail that created this massive hail scar kind of near Rapid City, South Dakota. And this hail scar was so large that in some parts it was 6 miles wide. And with the daily surface reflectance data, we can watch how the land heals over the scar and also what changes occur around the scar during the period of about a month or 2. So let's watch. So here we can see the scar begins to fade. It fades even further and further. And not only are we seeing the hail scar fading, but also the vegetation around the area is kind of drying out and becoming a little more sparse towards the middle to late August in the area. So now that you know what to expect, let's run through that one more time. So we have before the hailstorm, and then we can see the hail scar, and we can see it as it's starting to fade. So it's going to provide a pretty unique view to observe the land cover and vegetation changes that are occurring from this storm. And these data can help us understand where a storm existed, what areas might have been hit the hardest and sustained the most damage. So speaking of vegetation, let's cover vegetation next. So the Vegetation Indices is telling us about the health of the vegetation, essentially how green the vegetation is. And now that you're an expert at product short names, you can decipher what these yellow words mean on the screen. So the VNP13A1. So that's going to tell us that this is a VIRS vegetation product. And these products are available as 16-day in 500, 1,000, and 5,600 meter resolution, and in monthly in 1,000 and 5,600 meter resolution. And the 3 main layers for this product are the Normalized Difference Vegetation Index, or NDVI layer, which is one of the longest continual remotely sensed time series observations using both the red and near-infrared bands. So VIRS is continuing that NDVI legacy. And then the Enhanced Vegetation Index, or EVI layer, which is a little bit more sensitive to canopy cover than NDVI. And finally, the EVI2 layer, which is a reformation of the EVI layer using the red and near-infrared band. So let's examine NDVI at 2 different areas in the world. So here we have a map showing the NDVI layer near the Nile Delta. We have the vegetation in the center, and it's primarily surrounded by deserts and water, so in this case, the Mediterranean Sea. And we can see that the NDVI values in the vegetation are a little bit lower when we compare them to an area like the dense Amazon rainforest. So here we can see the darker green colors, which indicates a healthier vegetation. And we can actually track and see where water banks and communities might exist where the vegetation is lower in those NDVI values. So now that we've looked at the health of the vegetation, let's look at LAI and SPAR. So this product provides more information about the vegetative canopy itself, and it's currently available as an 8-day composite at 500-meter resolution. And first we have the leaf area index, or LAI, which quantifies the one-sided leaf area of the canopy. And then we also have the fraction of photosynthetically active radiation, or FPAR, which is the fraction of incoming solar energy absorbed through photosynthesis at 400 to 700 nanometers. So let's go ahead and examine that LAI a little further. So here we have the LAI of the country of Germany from mid-February 2018. And to give you a little more context, all throughout the country we're seeing agriculture. In the northern and southern areas we have grassland. In the top right near the water, and a little bit below that we have an area classified as evergreen coniferous forest. Near the middle central we have mixed forest, and near this urban area we have deciduous forest. So let's see what LAI for the country looks like closer to summertime. So here we can see some of the values have dramatically increased during the summer, as we would expect. Again, all throughout the country we have agriculture. In the northern and southern areas we have grassland. The top right and a little bit below that is going to be evergreen coniferous forest. We have mixed forest, and then the most notable change is now the dark green area near that urban area, which is the deciduous forest. And remember these maps of Germany because we'll be seeing them a little later in the presentation again. So finally, let's talk about fire. So these data tell us about the location and intensities of fires. And we currently have a daily product at 750-meter resolution. Now this might sound a little odd to you since before I mentioned these data are resampled to match the MODIS resolutions, but this is actually swath data. And we are planning on releasing a sinusoidal gridded data very soon if you're interested in that product. You may also notice on the screen there's two different products listed here, the VNP14 and the VNP03 MODLL. And this VNP03 product is actually used specifically for geolocating the VNP14 swath data. And I think these data are really cool because they can also help us identify other thermal anomalies around the world. So for example, like where a volcano might exist. So let's see what these data look like. Here we have a VNP14 swath data image from August 9th, 2018 near the Democratic Republic of the Congo and Tanzania. And you can see a large amount of fires shown in red near the center left of the image. And then we can also see some vegetation, some clouds, and some water. We're able to identify where heat sources and fire exist. So those are the data products we're currently distributing, but what about the products that we have in the future? So we have several VIIRS products coming soon over the next couple of weeks and months, and even more next year. So in the future time frame, we have the 1,000-meter daily sinusoidal gridded thermal anomalies and fire product that I mentioned earlier. We will also be having some land surface temperature, or LST data, and these data are specifically about the temperature of the land surface, so they're not related to air temperature. And we'll also have that bidirectional reflectance distribution function, or BRDF, and albedo data. And next year, we're looking to release a land cover product and a burned area product that are similar to the currently existing MODIS products. So now that we've talked about the data, let's talk about citing the data. And we do ask if you are using the data, any data access tools, or any images from the LPDAC, please cite what you use. Each VIIRS product has its own DOI landing page, which has citation information, as well as a handy citation generator on each page. And then we also have the LPDAC website, which has the Citing Our Data page. So this section provides more information on examples on how to acknowledge and cite the data, tools, and any content you may use from the LPDAC. And we have the LPDAC website listed here if you need that information. So now that we've talked about the data and how to cite the data, how can you get your hands on this data? Well, we have several options depending on what type of user you are. If you're completely comfortable with data and you just want that original HDF EOS 5 and you just want to get started on your research, I recommend Data Pool or DAC to Disk. If you'd like to see a preview of your data before you download it, you want to make sure it's actually in your study area. You possibly want to do some customizations to your data, and maybe if you want to explore some other data sets that might exist in your area, I recommend using NASA Earth Data Search. If you really want to dive deep with the data and customize it and explore the values before you download anything to your computer, I recommend the Application for Extracting and Exploring Analysis-Ready Samples, or VIIRS. And in a few moments, I'll provide you with a demonstration on NASA's Earth Data Search and VIIRS. But first, if you have any questions while working with the data, our live in-house user services team are just a phone call or email away. And if you want to learn more about the data we've talked about today and get really into the nitty-gritty details, you can visit the LPDAC website where we have information about the data products as well as the user guides and ATBDs. And if you want to learn more about what new data are coming out, any new tutorials we're releasing, or how the data are being used, please feel free to join the LPDAC listserv. We send out an email about twice a month with updates on the data, any new e-learning items, and any new data and action stories as well. But with that, let's dive right into the next section of the webinar, the live demos of VIIRS and Earth data. So first I'm going to show you how to find 8-day composited surface reflectance data, or that VNP09A1 data, over the U.S. state of Arkansas from January 1st, 2018 using NASA's Earth Data Search. Then I will show you how I made those maps of Germany earlier in the presentation using VIIRS, and we'll explore LAI trends in that area. Okay, so on the screen you should see Earth Data Search. So what we're going to do is first you'll log in with your NASA Earth Data login account. So here you'll be able to log in with your account through the Earth Data login. If you don't have an account, don't worry, they're freely available to create, and when you click on the button, it will provide you with information on how to create your own account. So the very first thing we're going to do is zoom into our study area. And as I mentioned, we're looking at Arkansas, and we're looking at that 8-day composited VIIRS surface reflectance data from this year. So I'm going to zoom in, and then I'm going to type in VNP09A1 and hit enter. And then I'm going to set my temporal information. So I'm going to pick 2018, January 1st to today, and I'm going to apply this filter. And one cool feature of Earth Data Search is that you can always save your project. So if, say, you want to come back in November and see what the most recent data is, you can save your project and then come back in November and check it out. Next, I'm going to set up my spatial information. So I'm going to draw a polygon around Arkansas. So I'm just going to click to add my points, and then I'm going to close my polygon, and I can see that Arkansas has been selected. And now I'm going to verify that this is the product that I want. So it is that VNP09 data, and that is that 8-day surface reflectance data. So I'm going to go ahead and click on the View the Granule. And I can even start making a little analysis here. As I'm looking, I can see some previews of what these granules are going to be looking like. And as I'm scrolling down, I can see that it's starting to get, the vegetation starting to die. So it's getting a little browner during the winter time, as we would expect. So I can either decide that I just want the most recent data, so I can download this single granule, or I can go ahead and download all of these 34 granules. So let's go ahead and download all of this data. So I'm going to download the data, and it's going to be about 811.2 megabytes. And so I can either choose to directly download this data. So Earth Data Search will provide me the links that I can click on to download the data. I can stage the data. So let's say maybe I'm working from home right now and I'm not on my work computer. I can always stage it for delivery, and the data will be emailed to me either as a list of downloadable links or as a zip folder. Or I can choose to customize the product. So I can reformat and reproject and pick a couple other settings. And then if I choose the customization, again, that's going to email me once the data are ready. So that is a brief look into NASA Earth Data Search. It's a great tool for previewing your data and finding other data from your study parameters. Next, let's look at VIIRS. So again, VIIRS is the application for extracting and exploring analysis-ready samples. And VIIRS is a data subsetter that allows you to access data from a variety of federal archives in an easy and efficient manner. So using VIIRS, you can subset the data spatially, temporally, and by layer, as we will see. And VIIRS provides you not only the data values, but also the quality information. And it allows you to explore your data values and quality information via interactive plots and graphs prior to downloading any of this data. So let's go ahead and get started. And again, I'm going to sign in with my NASA Earth Data account. And again, if you don't have an account, you can just click on this button and they'll help you register for your free account. So I'm going to go ahead and click on Extract, and I can see I can either start an area sample or a point sample. So again today, I'm going to be creating those previous maps that we saw earlier of Germany. And I'm going to be looking at the Leaf Area Index, or LAI, in Germany from January 1st, 2015 to present. So today I'm going to select an area sample. However, if you work with flux towers or specific geographic coordinates, I highly recommend checking out the point sample on your own time. But for today, we're going to click on Area Sample, and you can either start a new request, copy a previous request, or upload a request file. And this request file I'll mention a little later in the demonstration. But for right now, we're going to start a new request. So I'm going to name my sample LAI, Germany, January 1, 2015 to present. And then I'm going to upload an Esri shapefile that I have of Germany. So I'm just going to drag and drop my shapefile into this box. And now I can see my map of Germany has updated. So I can see that there's a polygon selected around Germany. You could also upload a shapefile that contains multiple polygons, say if you work with different national parks or different regions. So I'm going to now set my temporal information. So I can click Start Date, and I'm going to change this to 2015, January 1st. And then for end date, again, I'm going to take to today because we want to see what the trends are up to present. Next, I'm going to add the layers to include in my sample. So I'm going to search for a product. So I'm going to type in LAI, and I can see some of the MODIS products that are available in the VIIRS. I'm going to scroll all the way down to the VIIRS product and click on it. And this is going to bring up all the layers that are in that VIIRS product. And if I want to learn more about a layer, I can always click on this eye to learn more about what the layer details are. So I know this is the layer that I want, so I'm going to go ahead and click on it, which has added it to the selected layers. If for some reason you accidentally add a second layer, you can always just click on it to remove it. And then we'll go to our output options. So for my file format, I can either have a GeoTIFF or a NetCDF4. For today, I'm going to pick a GeoTIFF. We also have our projections. So these projections work really well and are native to some of the data that are currently in VIIRS. I'm going to go ahead today and select Geographic. And then I'm going to submit my request. So now I can see that my request was successfully submitted. So I will receive one email that my request was submitted, and then once my request is ready, I will receive a second email saying that it has been completed. And that will direct me to this Explore menu. So we can see that my request is running, and I already ran a request just for the sake of time. So let's go ahead and click on View the Contents of this request. Okay, so as I mentioned earlier, if you do work with, say, national parks, if you had uploaded a shapefile that had multiple polygons, you can figure out which polygon you specifically want to look to, and it'll update the map to tell you which one you're looking at. For today, we just have the Germany shapefile. You can also do the same with layers if you added in more than one layer. Today, we're just looking at that LAI. So now let's examine the layer statistics. So I can already start to make some initial analysis. I will have to explore a little bit more, but I can see that it looks like in 2015, LAI wasn't as consistent as it was in some of the following years. I can also interact with this timeline below to pick the information and examine a little further in detail. And I can see that as I'm hovering over these box and whiskers, I can see what the actual LAI values are. I can also choose to look at just a specific year. So let's select 2016, and I can observe the trends in LAI just for that year. And I could also modify the y-axis range if I wanted to. And as I'm interacting with this chart, The charts below are also going to update, as you will see. So they're updating as well. And then below that, I have my decoded quality information. So if I hover over one of the colors, it's going to explain to me what these quality information mean, and these are based on the ModLand QA bits within the data. So this red section means the main method was used, best result possible, no saturation, so that's great, and the biome type is grasses and cereal crops. The green is, again, best result possible, no saturation, and evergreen needle leaf forest. So I can examine my QA information and my data values and decide if this data is exactly what I want and the quality looks good, I can go ahead and get ready to download this data. So I'm going to click on this drop-down, and then I'm going to click on Download. And now I can see the files that I can download. So I have this metadata XML, a granule list text file, so I know exactly what granules are going in my request, a README text file, so I can learn more about appears, how to cite appears, things like that, a JSON file, so if, say, I'm on travel and I want to make sure that my colleague who's at the office can see this request, he can go ahead and run this JSON request file, so I'll just email him the file, he runs it in appears, and he can see the exact same results that I'm seeing. And then also statistics for the quality layers, lookup values for those quality bits, and summary statistics as well. And below that, we have the geotiff, so we have the quality information, and then also the geotiff surface reflectance, or LAI data. And this is actually the files that I use to create those maps of Germany. So I just downloaded 2 LAI files from here, added them to my favorite GIS program, added a color map, and it was ready to go for my presentation. So as you can see, Appears is super helpful and easy, and it saves a lot of time in accessing, customizing, interacting with, and downloading data. And if at any point you need help with Appears, you can click on this Help menu button. So that provides documentation for Appears. It also provides the available products that are in Appears, and we're currently adding even more products to Appears. So if you don't see a product you're interested in, check back later. And then also the Contact User Services tab. So again, that'll direct you to those user services in-house staff at AROS. So next up, Cole will discuss a Python tutorial to show working with VIIRS surface reflectance data. Take it away, Cole.
All right, thank you, Danielle. Now that Danielle has introduced NASA VIIRS products and where to find them, I would like to dive a little deeper and show you all how you can begin processing and analyzing NASA VIIRS surface reflectance data in Python using a Jupyter notebook. In the interest of time, I will not provide a step-by-step execution of the tutorial, but rather I will first show you where to find the tutorial and then give an overview of the products or the topics covered. So here's the LPDAC website at lpdac.usgs.gov, and if you hover over User Resources and click on e-learning, our e-learning page contains a collection of digital resources to learn more about LPDAC data, tools, and services. Next, if I click on the Tutorials tab and type VIIRS into the search bar, you will see the Working with Daily NASA VIIRS Surface Reflectance Data tutorial with links to an HTML formatted output, which we'll take a look at in a second, as well as to the source Jupyter notebook, which will take you to the LPDAC Data User Resources Bitbucket repository. Just quickly wanted to mention here, at the repository, you can download links to the Jupyter notebook, the HTML formatted output, or you can preview the tutorial in the Markdown file. At this time, if you would like to follow along, go ahead and open the HTML format output, and I'll walk through the various topics covered today. This tutorial shows how to work with daily NASA VIIRS surface reflectance data. The tutorial shows some basic image processing principles, such as how to open and work with HDF EOS5 files, georeference and quality filter, visualize the results, and export as geotiff files. The tutorial converts the daily surface reflectance data into vegetation indices to examine the trend in vegetation greenness during a recent drought observed over parts of Central Europe. Before getting started, if you plan to execute this tutorial on your own, you will need a NASA Earth Data login account to download the example data used. You can download the data used in the first 8 sections from the LPDAC data pool at the link provided. If you are interested in Section 9, which covers working with time series, use the links to the text file or the NASA Earth Data Search query in order to download the daily data for the month of July. First things first, we will import a host of Python packages needed to execute the tutorial. I will try to highlight some of the major packages as they are used throughout. Next, define the input directory containing the VNP09GA version 1 HDF-EOS5 file. So again, if you were executing this tutorial on your own, you would need to update INDIR or input directory to wherever you have downloaded the example file on your own system. In the final section of topic 1, search the current directory for the VIRS file used in this example. For additional information on the VIRS naming scheme, be sure to check out the inset in the tutorial here. Topic 2 covers how to import and interpret the data. Begin by reading in the file using the H5Py package. The preceding sections show how to navigate and maneuver through the metadata contained in the HDF-EOS5 files. I did want to point out the struct metadata object, which stores the file metadata. Here we read the file metadata and store as a list. Some of the metadata you see here will be used later when we georeference the data. Lastly, walk through the directory tree, retrieve the objects, and append to a list. In Section 2B, the tutorial zeroes in on the SDS layers and SDS metadata. Here, we read in the datasets needed, including bands 3 through 5 and 7, which are the red, green, blue, and near-infrared bands. Next, read the SDS level metadata, including things such as the units, fill value, and scale factor. Topic 3 begins by loading in the data arrays and ultimately generating an RGB composite image. First, import the SDS array by calling the value from the SDS objects and then immediately apply the scale factor to each array, giving us scaled arrays of red, green, blue, and near-infrared surface reflectance. Next, use NumPy's NP stack to create a 3-dimensional array, which is needed to generate a 3-band RGB composite image. Section 3B uses the matplotlib package in addition to scikit-image's exposure module to stretch and plot the RGB composite. For this example, the tutorial performs a contrast stretch on the image using the 2nd and 98th percentile values and performs a gamma correction. Note that stretching the actual array will inherently change the values of that array, and thus this is for visualization purposes only. So here we use matplotlib to plot the result. Looking at this output, you will notice that the study region includes parts of England, France, Belgium, and the Netherlands, Germany and Denmark at center, Poland to the east, and then the southern reaches of Sweden and Norway. So this image is from July 2nd, 2018, and you'll notice here that there are shades of tan and brown throughout the image, which is indicating drought-like conditions as the vegetation is dried out during this normally summer or green time of year. Another thing you'll notice in this image is while it is relatively cloud-free, there are still clouds overcasting parts of the area. To calculate vegetation indices from the surface reflectance data, we will first need to remove those cloudy observations. So before calculating vegetation indices, the tutorial shows how to filter the data for clouding quality considerations. Topic 4 shows you how to decode bit values, determine which values to keep, and how to apply a mask to the data arrays. So the VNP09GA version 1 product is slightly different than similar MODIS products in that there are different quality SDS layers referred to as quality flags within each file. So QF5, or quality flag 5, specifically contains the overall quality determination for each of the bands that we are interested in, as shown in the user guide table 14 here. Last month, the ORNL DAC gave a great explanation on bit field mappings and how to read them, so I would encourage you all to check out their NASA Earth Data webinar from this past August. The basic premise to remember is that bits are read from right to left, and here we are interested in the 4th through 7th bits, which we want to be set to 0 for all. Below, set the number of bits and generate a list of all possible bit combinations, and then based on the information above, create a new list that only contains values where the unpacked bit value is set to 0 for bits 4 through 7. So you'll notice here if we print out the list of good quality values, the first 4 digits are always 0, which are actually the 4th through 7th bits indicating a good quality observation. The next section here uses NumPy's masked array functionality to apply a mask to the arrays. Notice that invert is set to true because we are inputting a list of good quality values that we would rather keep than exclude. Below, the tutorial runs through the same steps as above for the Quality Flag 2 dataset, which includes a land and water mask. Since the tutorial is looking at vegetation indices and drought, there is no need for us to keep the pixels over water, so apply another mask to the data to only include pixels over land. Topic 5 shows how to define functions for NDVI and EVI. Once the functions are defined, they are then executed below. For more information on creating basic functions in Python, be sure to read the inset in the tutorial. In topic 6, the tutorial uses matplotlib to first make some basic plots, then work your way up to more advanced plots, including a demonstration on how to export the plots as images. So here we have a basic plot of NDVI and of EVI. And then next, we add 2 subplots so that you can plot NDVI and EVI together, add some titles, and use the savefig functionality to export the figure as a PNG file. So notice here that NDVI appears consistently higher than EVI in darker shades of green, possibly due to oversaturation of NDVI in areas with high biomass. So section 6b shows how to generate a scatter plot to better characterize the differences seen between the VIs. Looking at this output plot, we do see a wide range of EVI values over many pixels where NDVI is very high, around 0.9. Topic 7 shows how to georeference the data arrays and export the results as geotiffs. Here you can see the tutorial uses the file metadata to find the upper left coordinates, define the output pixel size, and include the proj4 projection string for VIRS, which is actually the same as the sinusoidal projection string for MODIS. Section 8 shows how to export the output data arrays. However, before exporting the data, first set up a dictionary for the arrays to automate the process of exporting them. Here the tutorial uses a for loop to iterate over each dataset in the dictionary and uses GDAL to export the arrays as geotiffs using the georeferencing information we saved above. Section 9 is the final optional topic that takes everything that we went through above and wraps it into an automated time series analysis to look at the drought over time. Again, you will need to download all 31 daily VIIRS surface reflectance files from the month of July 2018 using the links provided in order to execute this portion of the tutorial on your own. Section 9a shows how to automate the steps that we just walked through above and perform each step for the 31 files representing the 31 days from this past July. Section 9b shows how to set up a data frame using the pandas package and ultimately calculate some statistics for each of the observations. Below, loop through each array in the time series and use NumPy to generate a host of statistics. Then export the pandas data frame containing the statistics to a CSV file. Next, the tutorial uses the statistics calculated above to plot a time series, including the mean, the standard deviation, and a linear regression trend line through the data. So, based on this plot, it appears that NDVI is decreasing throughout the month of July over our study region, which could indicate that the drought conditions were persisting or even intensifying throughout the month. Last but certainly not least, Let's create a visual time series observation for comparison. The final section of this tutorial is my personal favorite. First, we will import the image.io package to create a GIF of the daily RGB composites created earlier in Section 9 to visually observe the drought-like conditions taking place over the month of July 2018. So here we create a list of the RGB files and append them to the GIF image. This will create a GIF of the images in that list. Lastly, let's look at the GIF. So using this visual aid, you can watch the landscape turn shades of tan and brown throughout the month, which matches the statistics seen above. Thank you all for your time, and again, this tutorial is publicly available at either our e-learning pages and on our Bitbucket Git repository. All right, Jennifer, back to you.
All right, thank you, Cole. Thanks, everybody. So at this point, what we'll do is we'll transition to a final set of polling questions. And we'll give these questions about 3 to 4 minutes or so, and then from there, we'll transition to our Q&A period. So if you asked a question a little earlier on, not to worry, that'll be captured, and we can address those in a few minutes here. So thank you very much, and let's give these questions about 3 to 4 minutes or so. All right, thanks, everybody. This is really excellent feedback, everybody. And so we're going to give these just another minute or so, and then we'll jump into the Q&A period and, have a go at the questions. All right, thanks, everyone. Okay, everybody, thank you so much for your input. At this point, we're going to transition to the Q&A section of the webinar. And just really quickly before we do that, I wanted to draw your attention to two of the pods you'll find in the lower right-hand corner of your screen. The first is below the Q&A, and it is entitled VIRS Land Products Useful Links. There are links to many of the portals that were mentioned earlier. I know that one of our participants had a question about that. And some of the scripts and tutorials that were also mentioned are linked here as well. This is a persistent feature. If you access the webinar by way of the direct link, which I will send to everybody within a couple of days. And then below that, you'll find the presentation file. The PowerPoint has been uploaded and is available for you to download. You would highlight the file, and you'll be prompted to download that presentation file. And then finally, the agenda, which I spoke to but did not show, is also there as well for reference. So with that, let's go ahead and get started here with any questions. Taking a look here. Okay, so hopefully there was a question about whether or not we would post the links to the portals at the end, and hopefully those that you were looking for have been mentioned in the file sharing or the useful links pod. If not, please feel free to enter additional information here. Does anybody have any questions? If you have a question, type those into the Q&A pod. Works like a chat, and we'll be able to get to those.
And while they're getting those in, this is Danielle. I just wanted to mention, under the useful links, we have that link to the e-learning table. And we've released a couple of videos about VIRS data too. So if you're interested in learning more about VIRS surface reflectance data, we have a three-part video series that's listed under the e-learning table. And we're releasing more videos upcoming in the next couple of weeks and months as well.
That's an excellent point. Thank you. Okay, so we do have our first question here. Are the thermal data from VIRS comparable to MODIS? If different, why? So did you guys hear the first question? Are the thermal data from VIRS comparable to MODIS? If different, why?
Yep, so currently we do not have the VIRS thermal data, like the VNP21s. However, to our knowledge, those products will be configured so that they are very similar to the MODIS products. We will keep you updated once we have access to those products and when they become publicly available.
Okay, are there any additional questions? I did want to note really quickly, though, that there are VIRS near real-time thermal anomaly fire data available through NASA firms. And Paul, I could certainly email you a link to, we held a webinar, I think it was in June, and the operations manager for NASA's land atmosphere near real-time capability for EOS was the presenter. Her name is Diane Davies, and so I could certainly email that, which might provide some information if that interests you as well. Okay, just looking to see if there are additional questions. Any additional questions? Let's see. Scroll down here. Are the thermal data available in raw form? Follow-up question.
So in regards to the thermal data in raw form, we do have the VNP14 product, which is the SWATH VIRS Fire and Thermal Anomalies product. But in regards to the land surface temperature product, like the VNP21, we do not have access to that yet, but we will keep you updated. And then as Danielle had alluded to earlier, we do have a gridded VIRS Fire product, the VNP14A1, which we are currently in the process of making publicly available. So please keep an eye out for that one. That one should be coming out fairly shortly.
Okay, well that's very good feedback. Thank you, Cole. Are there additional questions from anybody? All right, let's see here. All right, let's see. All right, here is the next question. If both MODIS and VIIRS have a leaf area index product, which is better?
So that's an interesting question. Unfortunately, we haven't done like a comparative analysis between the two products. We do know that both products are available and that we have users that are working with both of those products. But no, in terms of picking a favorite or which one's better, I would just say that they're similar products, and there has not been a comparative analysis between the two.
Okay, thank you. I mean, the other thing too that we could do, Allison, is I can email you a link to data product documentation for you to kind of compare the difference between the two. That might, shed a little bit additional light on, kind of determining which product you might be interested in using. Are there any additional questions here? Let's see. Okay, well, while we're waiting, just a couple of final notes. Again, what we'll do in the next couple of days, I hope to have this post-processing completed and have the webinar uploaded to our NASA Earth Data YouTube channel. And you'll see some information there on the left-hand side on the thank you slide. And I'll send a direct link to the recording out to all of the registrants. So if you have colleagues who are unable to attend due to time conflicts, and certainly they'll be able to take a look at a later date. And then again, if you're interested in downloading either one of the agenda or the file, you would highlight the file in the lower right-hand corner of your screen, and you'll be prompted with an option to download that file. And I'll give it another look here. If there are no further questions, what I generally do is I'll leave the virtual meeting space open an additional 10 minutes or so for people if you think of a question or you're interested in downloading links, downloading the presentation files or checking out any of the links, and then we'll hang up from the audio component. All right, let's take a look. Any additional questions? Okay. Well, thank you very much to our speakers, Danielle and Cole, today, and thanks to all of you for participating. Our next webinar is actually on an entirely different, focused on physical oceanography data, and that will be held on October 24th. And the focus will be on, transitioning from FTP access for the physical oceanography data products to HTTPS, and our scientists and user services staff at PODAC will walk participants through those changes. Okay, well, thank you so much, everybody. If there are no further questions, I'll give it another look. We will log off from the audio. Thank you. I'm glad that you found value in this webinar. Thanks to everybody. We'll log off from the audio components, and I will leave the virtual meeting space open for 10 minutes. All right, so if you think of something, don't be shy. Type it into the Q&A.
Thank you, Jennifer.
Everybody. Thanks, Danielle. Thanks, Cole. We'll talk later. All right. Bye, everybody.